Hi everyone, in this section we're going to talk about global climate change, which per College Board has a lot of subtopics to it. So this ties in a lot of the little topics we've talked about within this unit and expands upon them a little bit more. So if you've heard some of this information before, that is by design because this section is kind of a smorgasbord. So let's talk historic climate change. So Earth's climate has varied over geologic time, largely due to variation in Earth's orbit around the sun. So the Earth can vary in obliquity, which occurs about every 40,000 years, which can expose northern latitudes to higher insolation at different times. So that obliquity is Earth's tilt on its axis. So we say it's about 23.5 degrees, but it actually kind of wobbles on its axis. So that degree can change every so often, but it does not happen very frequently. We can also have variations in eccentricity. This occurs every 100,000 years or so, which brings Earth closer to and further from the sun at different times. Earth's orbit around the sun is not circular, it's actually an ellipse. So when we're talking about changes in eccentricity, we're talking about changes to the orbit shape. So as that ellipse elongates, the Earth will generally or on average be further away from the sun, and as that ellipse shrinks, it'll be closer to the sun. So that can cause climate change as well, and that would be naturally occurring. Scientists have measured and estimated Earth's historical temperature and CO2 levels using three main pieces of evidence: foraminifera shells and ocean sediments. So different species have different temperature tolerances, so the appearance of these shells in certain time periods can indicate a certain temperature of the ocean water. Air bubbles and ice cores that contain ancient atmospheric gas, which indicates CO2 levels, and oxygen 16 versus oxygen 18. These are isotopes, and these have certain concentrations in ancient ice. Increased oxygen 18 concentration typically leads to or is correlated with an increased temperature for that time period. So this is kind of what it looks like over time. So this graph shows years before present day. We've got carbon dioxide levels in blue and temperature of the planet in red. And you can see over time, scientists have figured out that the climate of Earth has naturally fluctuated. We've had periods of hot and periods of cold, periods of higher CO2 levels and periods of lower CO2 levels. And the causality for the CO2 level rise are strongly correlated with temperature, but that causality isn't fully understood. When we're talking effects of climate change, this is anthropogenic. So those ebbs and flows with the change in temperature, mostly for the natural climate change, happen over a very, very long period of time. But we have seen since the Industrial Revolution a rapid increase in overall temperature of the Earth. These slides are going to talk about the effects of climate change relating to anthropogenic climate change. So rising temperature can lead to habitat or species loss, drought, soil desiccation, heat waves, increased precipitation in some regions. Rising sea level we talked about in the last section. This is typically due to glacial and continental ice sheet melt, plus thermal expansion of the water. We talked about the effects of that in the last section, so I'm not going to get into that too much here. We've also talked about melting of permafrost, which is the permanently frozen tundra soils that begin to thaw and release methane and carbon dioxide from anaerobic decomposition, and this occurs seasonally. So with rising temperature, we can lose that layer of permafrost altogether. This visual here just shows the risks of global warming to an increase of 2 degrees Celsius. That seems to be the hot button temperature when we talk about global climate change. So the grayed out area is 2006 to 2015 relative to pre-industrial levels. So if we were to increase the Earth's average temperature by 2 degrees Celsius, we are looking at a threat or a very high threat for ecosystems. We can increase weather extremes, corals going to die off, there's going to be huge impacts to Arctic regions, coastal flooding is going to be of a concern, as well as flooding elsewhere, and then crop yields will decrease as well. So we can have this huge sweeping effect across the globe if our planet ends up warming 2 degrees Celsius. So impacts on coastal communities, we can have property loss and damage, and then we might need to have those people potentially relocate. We talked about this in the last section as well, but this is of concern for poorer communities along the coast that may need to relocate inwards. Sometimes it's just not feasible financially for those people to move themselves inland. Seawalls or other barriers can be built, but this just delays the eventual flooding. Loss of barrier islands. So these are islands that buffer coastal communities and ecosystems from wind and waves, and may be lost as sea level rises. So this just kind of demonstrates what sea level rise can do to certain areas of a coastal community. We can have an impact on atmospheric currents when we're talking global climate change. So we can have a widening and a weakening of the Hadley cells. Remember, those Hadley cells are those atmospheric convection currents that occur just above and just below the equator to 30 degrees north and 30 degrees south. As temperature differences between the equator and poles decreases, the air ascending and expanding from the equator travels further before sinking. This shifts subtropical zones, so these are your dry desert biomes, toward the poles and expands the tropic. Regions between 30 degrees and 60 degrees, so where the current feral cells are located, may experience drier climate as cool, dry, descending air from the Hadley cell shifts north and south. We can have a weakened or destabilized jet stream. As the Arctic regions warm faster than other areas of Earth, the temperature contrast between the equator and poles that drives the jet streams decreases. A small temperature difference between the poles and subtropical regions leads to weaker, wobblier jet streams. This causes extreme cold spells in the eastern U.S. and dry spells in the western U.S. This happened with that polar vortex we experienced a couple of winters ago. So global climate change has actually destabilized the jet stream, which allowed for that really, really cold winter. I feel like the year 2016 is sticking out in my head, but I don't think that's right. But we did experience that really, really cold winter, and that was mainly due to the weakening of the jet stream. Impacts on marine ecosystems. So we can have altered range of marine ecosystems. Some new marine habitats will be formed by rising sea level flooding the coastline. Some areas of the ocean will become too deep to receive sunlight, and the photic zone will shift upwards further from the ocean floor, and this throws a ton of organisms outside their range of tolerance for sunlight. The altered ranges for those organisms, so warm water holds less oxygen, so the aquatic organisms actually breathe the dissolved oxygen in the water. Warmer water holds less oxygen, so many fish populations have declined or migrated to cooler waters because of this. Ocean circulation, so we talked earlier this year about thermohaline circulation. So this is the global ocean current that redistributes heat from the equator, as well as salt and nutrients, and mixes ocean water. This could end up slowing or stopping altogether. Ice melt from Greenland leads to especially cold freshwater buildup in the North Atlantic. Freshwater is less dense than salt water, preventing it from sinking. And this cold water from the North Atlantic slows warmer Gulf stream waters, which cools Europe and slows global thermohaline circulation. So we won't get as much upwelling, we won't get that transfer of nutrients or that saltwater movement across the globe. And this is what we saw earlier this year with the thermohaline circulation. And these would be your differences in temperature based on the distribution of that thermohaline circulation. Unequal global warming. So polar regions of the Earth are warming faster than other regions. This is called polar amplification. This affects the Arctic or North Pole because there's more land and less water to absorb heat. So water has a very high specific heat, meaning it takes a lot of energy to raise the temperature of 1 gram of water 1 degree Celsius. So land is going to heat faster than water. So the North Pole tends to heat up faster than the South Pole. Melting sea ice means more exposed ocean water, which absorbs more sunlight than ice and snow, leading to more ice melting. This is a positive feedback loop. And the distribution of tropical heat to the poles by thermohaline circulation is also warming the poles. And these are just diagrams of all of that information. The melting of permafrost, so we talked about what that was. So air pollution adds soot and other particulate matter to the atmosphere and is distributed to the poles by atmospheric circulation. Darker soot or particulate matter covered ice absorbs even more heat due to lower albedo, creating another positive feedback loop. On polar ecosystems, so Arctic sea ice loss means habitat loss. So seals use that ice for resting and for finding holes to breathe. Algae grows on the ice, forming a base of the Arctic food web. And polar bears use ice for hunting seals at breathing holes. So this is kind of an entire Arctic food chain that would be lost because the habitat itself is lost due to the melting of the ice. And that is it for this section. If you have any questions, let me know.